Okay. So today we'll look at the derivative of a composite function. So what do you mean by a composite function? So let's say you have some quantity z that depends on two quantities u and v. Okay. And u and v themselves are functions of two other variables x and y. So u is a function of x and y, and v is also a function of x and y. I'm just calling those functions as phi and psi. All right. So technically speaking, you can write z as a function of two functions of x and y. Okay. So this is what we call a composition of functions. U and v are themselves functions of x and y, and z is a function of u and v. Okay. So if you have to find partial derivatives of z with respect to x and y, what do? Well, one thing we can do is replace u and v inside this functional form. Am I audible? Did my voice break just now?
It's fine.
Huh? Yeah.
The audio is fine.
1 second. Yeah. So let's just look directly at an example. So let's say z is equal to u cube v cube plus u plus 1. And u itself is equal to x square plus y square. And v is equal to e power x plus y plus 1. Okay. And the question is to find del z by del x and del z by del y. Okay. So what would you do here? I'm not going to sit and differentiate because it looks horrible, but still what you could do is just in the given expression, replace u and v with the given expressions. You have x square plus y square whole cube, e power x plus y plus 1, the whole cube, plus x square plus y square plus 1. So you get a very ugly function in x and y, okay, which you have to differentiate, and you can find del z by del x, del z by del y, but it looks kind of like a pain. Okay, what else could we do? Okay. So is there something else we could do in a case like this? Well, we could look at something, an alternate way of looking at it. We could either do this, or what we could do is we could write an expression for differential of z in terms of u and v first. Okay, so let's see what we get. Dz is del z by del u by del u du plus del z by del v dv. Now we could write du in terms of its variables. So du can be written as del u by del x dx plus del u by del y dy, and dv can be written as del v by del x dx plus del v by del y dy. Okay, so plugging this back into dz, what do we get? We get del z by del u times del u by del x dx plus del z by del u du by dy sorry, del u by del y dy plus del z by del v by del x dx plus del z by del y, del z by del u. Why did I write v first for some reason? No, it's fine. Del v by del z by del v times del v by del y dy. Okay, nothing very, very fancy I have done. Basically wrote the differentials for all the three quantities in terms of their direct variables, and then substituted these two here. Now remember, what was our task? Our task is to find del z by del x and del z by del y. Okay, and we have managed to write dz in terms of dx and dy. Can we use this somehow to find the partial derivatives with respect to x and y? Has this helped us at all in solving our task here, in doing our task? Maybe I'll rewrite this in a slightly different way. So I'll collect these two terms together. Why? What am I doing? 1 second. Okay. So I collected the coefficients of x separately and dx separately and dy separately. Okay. Now is there any observation you can make?
Yeah, the terms with the dx or dy, they are equal to the whatever you get by partial derivating z by x or y.
Correct. See, that's the whole idea. If you had done this, godforsaken thing where you substitute u and v in z and get this jumbo thing here, if you do that and finally you write the differential in z, that differential will be something into dx plus something into dy, and that something is the partial derivative of z with respect to x. It has to be, right, according to the total differential thing that we learned before. Okay, so we can make the identification that this guy here has to be del z by del x, and this guy here has to be del z by del y. Is this clear? Panchami? Is my audio quite bad or?
The audio is
Okay. Fine, because it keeps telling me internet is unstable, etc. Okay, so let's try this in our previous problem. Okay, let's take this guy again. And again, it's not going to be extremely simple, but it will be more organized. Okay. So let's just find partial with respect to x. Okay. So what do we do? First, differentiate with respect to u, and then differentiate u with respect to x, and then differentiate z with respect to v, and then differentiate v with respect to x. Okay, so let's do this. So z with respect to u, could you differentiate and tell me, Ashlyn?
You said Z with respect to you, right?
Yeah. Yes.
Is it dou z by dou x,
Uh,
the LHS, left hand side?
del z by del x, yeah. See, the question is to find partial of z with respect to x and partial of z with respect to y. That's the question. Okay, so the idea is, see, did you get the whole point here? You could, if you want, write explicitly z in terms of x and y by substituting, and then differentiate this guy here, this monster. Okay, or you could follow this process where, was this derivation kind of, did it make sense?
Yeah, it did.
So I'm just using that here. So del z by del x should be del z by del u by del x plus del z by del v by del x. See this?
What I was thinking is, you said that it can, I mean, it's a bit foolish. You can cancel dou u by dou u and dou v by dou v. I
You
mean,
can't.
one.
You shouldn't. You shouldn't.
No. It you said it will work out. It shouldn't actually. It is foolish, but it should work out.
When did I say it should work out?
Wouldn't
I mean,
that become 1 is equal to 2 then?
No, no. You're talking about the signs. I think it was during Dirac matrices.
So that is why we make a distinction in the symbols. Okay. So when you have a derivative, when you have a function of one variable, the differential, the derivative is given as dy by dx. Okay. So in this case, this is chain rule for one variable. You can think, you see, you use the same symbols that you use for differentials, correct? Okay, so differentials actually have meaning in isolation. What I mean is, if I just write dy, it's a valid thing to write down. It has a mathematical meaning. It's a differential. And in one of the classes, I defined to you what a differential is, like two classes back or something. Okay, but something like del z in isolation doesn't have any meaning. Okay, so del by del x is an operator which has meaning, which makes sense only when you put a function of x comma y or x comma some other variable in front of it. Okay, unlike derivatives in 1D, derivatives in single variable where you get this. Okay, so if it was single variable and if you have d's instead of del's, so if you have del y by del x into dy by dx into dx by du, let's say dx you can cancel out. But you can't do that with partial derivatives. Okay, because you cannot think of dx's as independent, isolated entities for partial derivatives. Understanding?
Yeah.
That is why we use different symbols. Okay, it's very important to realize that there is this crucial distinction between total derivative and partial derivative. Okay, or derivative in one variable calculus versus multivariable calculus. So here that doesn't work. So good point. That doesn't work. Please don't cancel du here. Then you will get del z by del x plus del z by del x, which is 2 del z by del x, which is wrong. Okay.
Yeah.
Perfect. Yeah. Okay. So now let's do this. Yeah. Where did Ashlyn came back? Ashlyn? Nope. Yeah, Karthik, you only tell me del z by del u.
Yeah, 3u square v cube plus 1.
Okay. Tell me del u by del
2x.
Right. Del z by del v.
3v square u cube into it's just e to the power x plus y.
Perfect.
Times 1.
Perfect. Good. So this is the answer. Now, if you want, you could substitute u and v and you would get again an ugly thing, but the differentiation is done. Okay. Isn't this, you see the advantage of this, right? Isn't this way easier than having to deal with this guy? Right? Okay. So let's look at some more problems. Example 1. Example 2. Z is log of u square plus v, and u is e power x. U is e power x plus y square. V is x square plus y. Okay. I want del z by del x and del z by del y both. Now your answer could be in terms of a mixture of u, v, x and y. In terms of u, v, x and y. It's okay if your answer contains u and v. No issue. Any person can, if needed, substitute x and y for it. Substitute it in terms of x and y. Try this out, please.
It's x plus y square, right? Not the whole square.
X plus y square, not the whole square. If you're done, let me know in the chat that you're done.
Do we need to substitute u and v, or is it fine if we keep it as?
No, don't substitute.
Yeah, fine.
Yeah.
Done.
Yeah. The whole point of this way of finding partial derivative is that we avoid unnecessary labor. Okay. So substituting u and v anyone can do. Nishit, done?
Yeah, done.
Okay, so tell me, del z by del u is what?
Yeah, del z by del u is 1 by u square plus v to 2u,
Mhm.
and then del u by del x is e power x plus y square,
Perfect.
and then plus 1 by u square plus v, 2x, because 1.
Correct. Okay.
Yeah, and then del z, del z by del y is 1 by u square plus v, 2u, e power x square plus y square,
Huh?
2. Sorry, e power x plus y square, 2y,
Perfect.
plus 1 by u square plus v. That's all, right?
Perfect. So we can generalize this to more number of variables. So for example, if your function generalization, if your function, which I'll call a z, is a function of, let's say, u1, u2, etc., n variables, okay, un. And each of these u's is some function of x1, x2, etc., some m variables. Okay, it's not necessary that n has to be equal to n, right? Now, if you have to find del z by del xi, what would you have to do? First, differentiate z with each of the direct variables, okay, and then differentiate that variable with respect to the xi that you want here, and add over all the values of j going from 1 to n. Did this make sense? It's exactly what we have done above. What was, if you have to say this in English, what would you have said in the previous question? Okay, first differentiate z with respect to the direct variables, which are here u and v. Then multiply them with the derivative of those variables with respect to whatever you want here. So here you wanted x. So you differentiated u with respect to x and v with respect to x. And then you get a bunch of terms, add them all up. Okay. So similarly, if I want del yeah, so this gives you all of it. So now this can be thought of in a slightly different way. People often, sometimes some books write this in a matrix kind of notation. So I'll do that for two variables. Okay. So in the above case where we had u and v, and then so some function z depending on u and v, each of them depended on x, y. Okay. And what we wanted was del z by del x, del z by del y. So if I write this as a row matrix, I can write the result here as two variables. I'll just try this out. Del z by del u, del z by del v times del u by del x, del v by del x, del u by del y, del v by del y. Okay, will this work out? Check, please. Now, how do you multiply? This doesn't make sense. Right. 2 into 2, you end up getting 1 into 2. Yeah, perfect. Yeah.
Yeah, works.
Yeah, it works. It works. Yeah. Perfect. It works. Okay. So if you have a larger number of variables, you could just extend the matrix's size will change. Okay. So what will happen if, for example, you have u and v, which depend on x, y, and z. Oh, no, x, y, and t, let's say. Okay. So if it was a little different, z depends on u and v, and each of them depend on x, y, and t, 3 variables. Okay. Then the derivative with respect to the last variable, that is del z, del x, del z, del y, del z, del t. If I write that as a row matrix, that should be equal to del z by del u, del z by del v times del u by x, del v by del x, del u by del y, del v by del y, del u by del t, del v by del t. Okay, so let's just see. Yeah, perfect. It's working. Okay. This is just a notation. You might think that we are just complicating things, but people often use this as an expression. And the point of this is you again simplify the notation further. So often this is written as del of z with respect to x comma y is equal to del of z with respect to u comma v times del of u comma v with x and y. Okay, so what does this mean? These are just ways of shorthand ways of denoting the matrices I have written up there. Okay, so the ones with which you are differentiating with respect to, they are written as the rows, and the ones above are written as columns. Okay, so for example, how would you write this one? Could you make that, observe the pattern here and tell me, Sarvan, how should I write this in that notation?
Wait, what?
Did you get this notation?
The summation one, right?
No, this
or
is
the matrix.
Matrix. This is a new notation that I created right now. Not I, but this is like for you guys that I created right now. Not understanding this.
Okay, wait. I'll try first. If I'm wrong, it's fine. Dou z by dou bracket x y t. Then dou z by dou uv, and then above it's also dou uv, and then below it's dou x y t.
Okay. Do you see the beauty of this shorthand notation? Now it kind of works like our single variable derivatives, where this would cancel out and give you del z by del xy.
Yeah.
That's the point of giving this notation. So it's again, now you made something that was not very user friendly to something that is more user friendly. But we have to remember this is just mnemonic. Okay, it's a way of remembering it. It's just a notation. You can't actually do this without actually writing these matrices down. So finally, starting from here, you have no choice but to write the matrices and get each of those terms separately. Okay, so for all practical purposes, where you're given a function and you have to find partial derivatives, this is good enough. But when you want to communicate with someone about something in general, instead of saying, oh, all these terms are there, you just give this notation and it is understood. Clear? Okay. So, all right. So, any questions?
Regarding the previous notation, that summation notation. Is it UI or UJ?
It's UJ. See, I is what? I is giving you the name of the variable number with which you are differentiating this whole thing. And you are summing over the various g's, which means if I write this out explicitly, what will I get? Del z by del u1, del u1 by del xi, plus del z by del u2, del u2 by del xi, plus etc. Del z by del un, del un by del xi. So in each of the terms, notice the second derivative is always with respect to the second derivative there in the term is with respect to xi, because what you want here is with respect to xi. Understood?
Yeah.
Right?
xi remains.
That's why
xi remains the same, right?
xi remains
in case of
exactly. You can change whatever I you want here. So if I is 1, then all of these you can write it as 1. If I is 2, write all of them as 2. So I is a free index here. It's not a repeated index. You're not summing over it. Understood? So actually in the summation notation, you would write this like this. Okay. In the summation notation, you would write this as del by del ui z del del by del uj z del uj del xi. You don't have to write this sigma, and you see very clearly that these are contracted indices and you have to sum over them. Okay, so the sum is over j. Okay, so now let's look at a related idea, which is called the total derivative. Now, this is something that caused me at least a lot of confusion when I first learned this. Okay, I thought there was in multivariable calculus something called partial derivative and something called total derivative, but that's not the case. Okay, you have seen this before, probably, that's why I'm saying this. So the total derivative is something that is defined in very special cases only. Okay, so and what are those special cases? Let's say you have a quantity z which is a function of u which is a function of x, y, t, let's say. Okay, and there is a relation between x, y, and t, which means x, y, and t are not really independent. Okay, so for example, maybe x is a function of t and y is a function of t. So if you explicitly write the function in terms of t, how many variables does this function actually depend on? At the end, it depends only on t, correct? So you may at first sight feel that it depends on 3 variables, but since x and y also depend on time, eventually you will notice if you substitute that z is actually a function of t alone. So this is since a single variable function, you can define derivative of z with respect to t, not partial, the ordinary derivative. Okay, and this is called the total derivative. All right, so total derivative is defined for functions of one variable only, but in certain times you may have to write it, you may choose to write it in terms of several variables. For example, x and y could be coordinates, z could be some quantity, x, y, and x and y could be some coordinates, and t could be time. Okay, and the particle could be moving along a trajectory. Let's make it very specific. So let's say this is the potential energy. We are talking about potential energy as a function of x, y, z, points in 3D space and time. Okay, and x, y, z themselves might be functions of time. Okay, what physical state situation would this stand for? Let's say we have a charged particle moving along some trajectory in 3D space. So its position is given as a function of time. All right. So the potential energy here is a function of 4 variables, including time, and the position itself is a function of 3 variables, the position, because the charge is moving around in some specific trajectory. So you can define something like du by dt in this specific situation. Okay. So what does total derivative mean here? It's not just total derivative of the potential energy. It is the total derivative of potential energy for a particle moving along a specific trajectory. Clear? If all you have is the potential energy or electric potential, whatever it is, some field you are given, and there is no talk about any particle moving around, then if I ask you what is the total derivative of u with respect to t, it won't make sense, because x, y, and z and t are independent variables then. Okay, If all you have is potential as a field spread out, defined at different points in space and time, then total derivative with respect to time wouldn't make any sense. But if there is a particle moving around and you are looking at the effect of the potential on that particle, then x, y, z would be functions of t. Is it making sense? So total derivative is not a very general concept. It's useful in specific situations only. Okay. All right. So let's look at an example. Simple that way. So let's say z is x square plus root y. Okay. So at first sight, z looks like a function that depends on two variables. But what if there is a constraint? X and y are not really independent, but they are connected as y is equal to sine x. Okay. Now you can define something like the total derivative. If you want, you can sit and take partial derivatives, but in this specific case, since y and x are not really independent, you can write z as a function of one of those alone. You can choose either x or y, depending on whatever you want. Okay. So at the end of the day, z is a function of only one variable. So you can define derivatives with respect to those variables. Okay, this is the question. Not partial derivative, total derivative. Okay. So how will we do this? Well, one way is to just substitute here, but that's the brute force method. We won't do that. So here you see we have dz, which is del z by del x dx plus del z by del y dy. Okay, but y is a function of x, so you can write dy as dy by dx into dx. Correct? So if I substitute that back here, I get dz is equal to del z by del x dx plus del z by del y dy by dx dx. Okay. Now since I want del z by dz by dx, I divide both sides by dx. Okay. So I end up getting this. So our job is just to find this. Okay. Or, maybe if this was a little confusing, I'll do it slightly differently. No, that's actually the same thing. So dy by dx can be written as del y by del x plus del y by, del y by dz by dx can be written as del z by del x plus del z by del y dy by dx. Okay. It's not a new rule, it just came as a result of the previous things we have learned. All right. So could you do the same thing for this guy and find out both of them, dz by dx and dz by dy? Try it out, please. If you're done, tell me in the chat, please. Just check the first one. If you got that right, that means you understood, you can do the second one. Rion, did you get dz by dy?
It's del z by del y plus del z by del x into dx by dy.
And let's calculate this. Okay, so del z by del y is from the expression, what will you get, Rion?
1 by 2 root y.
Good. 1 by 2 root y plus, yeah.
Plus 2x.
What is dx by dy?
Dx.
This is one variable function, isn't it? Y is equal to sine x.
Yeah.
Yeah.
1 upon 1 minus y square.
Okay. X is sine inverse of y, and dx by dy is 1 by root 1 minus y square, correct?
Yeah.
Okay, fine. Into 1 by root 1 minus y square. Okay. Now let's finally write everything in terms of y. So you get 1 by 2 root y plus x is sine inverse y divided by root of 1 minus y square. Okay, is this correct? Others got the same thing? Panchami? Yeah, okay. Cool. Okay. Now, the last thing for today that I want to talk about is implicit differentiation. Okay. So the reason I'm just giving you the terms in the very beginning is all of these have their counterparts in one variable calculus: chain rule, composite functions, implicit differentiation, etc. So you already know what these mean. I'm just looking at their extensions in multivariable calculus. Okay. So let's try, just recall how implicit differentiation worked in single variable calculus. So instead of giving y as a function of x explicitly, I could give a constraint relation between them. So something like, for example, x square plus y square minus 1 equal to 0. Okay. So this expression is given to you. If you want, you can rearrange and write y in terms of x. But without doing that, can we find dy by dx? And yes, I'm sure all of you know how to do that, right? Ashlyn, without writing y in terms of x, how would you find dy by dx?
Just differentiate.
Very good.
2x into.
Go ahead.
2x into dy by dx.
2x into dy.
Dx square. No, sorry. 2x plus 2y dy by dx.
Correct. Equal to? Equal to 0. Okay. So you get dy by dx is equal to minus x by y. Perfect. Now, if I make this formal, what exactly did we do here? Okay. So the idea was, instead of having y as a function of x, you have some function of x comma y equated to 0. Right? From this example, you see that. So if you have f of x comma y equated to 0, basically that means y is a function of x or x is a function of y, assuming it satisfies properties of functions. All right. When you restrict it to certain domains, it will behave like a function. Okay. So now you want to find dy by dx. How would you do that? So what we have here is we have the expression for total differential df is del f by del x dx plus del f by del y dy. And how much should this be equal to? The differential. What does differential mean? As you vary x and y, by how much does the function change? That is what the differential represents. Okay, that's what you use it for. So how much would df be then, Sarvin? Can I equate this to something? Sarvin.
Oh, wait, what? DF, right? Okay, wait, I'm lost.
See, this part, did you understand?
Yeah. That part I got.
Got it. Now I'm just trying to formalize that. So what I mean is, instead of looking at a specific example, in general, what happened here? What did we actually do? Okay. So we were given with a problem like this. Some function of x comma y is equal to 0. Agreed? Look at this.
Yeah.
Yeah. Okay. So here f of x comma y is x square plus y square minus 1, and that is given to be equal to 0. Okay. So if I take a differential of this function, you would get the differential would be 2x dx plus 2y dy, correct?
Yeah.
Yes. And how much would this be equal to? Do you know how much it is going to be anyways already?
What is it going to be?
Is there anything further I can write down? Equal to what?
Equal to 0.
That's all. Okay, because the function value is fixed. This is a constraint, right? F of xy is fixed to be 0, so its differential should be equal to 0. Okay, all right. So here also, this should be equal to 0. So I can rearrange and write dy by dx is equal to minus del f by del x divided by del f by del y. Right? Okay. So what if there are more variables? This part we have learned in school itself. We know that. But more variables, what will happen? Okay. So let's say you have a constraint between 3 variables. f of x comma y comma z equals 0. Okay. Now let's say you have to find del f, sorry, there's a constraint between them. And this means you can write one of the variables in terms of the other two. So for example, this is a different way of writing, implicit way of saying z is a function of x comma y, isn't it? So if x, y, and z are related by some equation, then that means you can rearrange them and write z in terms of everything else. So for example, let's say you have sine x plus y square minus z equal to 0. This is in the form that I mentioned, some function of x, y, and z equal to 0. You can rearrange this and write z as sine x plus y square. And clearly z is a function of x and y. Okay. So whenever you have this kind of a relation, that's just a different way of saying z is a function of x and y. And therefore you can ask, what is partial z with respect to x and partial z with respect to y? Okay. Now again, we have two options. Either rearrange the equation and write it explicitly in terms of x and y and then differentiate. Or we do something very similar to what we did earlier. Keep the equation as it is and somehow find out the partial derivative. So what can we do? Okay, so first we will write the differential dz. Sorry, differential df of the function which is equal to 0. And that will be del f by del x dx plus del f by del y dy plus del f by del z dz. Okay. And because the function is always equal to 0, it shouldn't change. So its differential will also be equal to 0. Now, let's say I want to find del z by del x. I have this information with me. Can I manipulate this to find del z by del x? You have to use the meaning of what del z by del x means. So I'll tell you exactly what I'm asking. Look at this relation, okay? We found derivative of y with respect to x in terms of partial derivatives of the original function, which is equal to 0. I want a similar kind of equation here. But here it won't be the total derivative, it will be the partial derivative because z depends on two variables. Anyone?
If we remove the dy term and rearrange, will that give us the answer?
Why did you remove the dy term?
Because that's not part of dou z by dou x.
Exactly.
The variables are, yeah.
Very good, very good. So del z by del x means you are holding y constant and you are changing only x. Okay. So you can rewrite this expression when y is a constant. If you hold y constant, then you would get del f by del x dx. Okay. Or I'll do one thing. Okay, so let's hold y constant and you get del f by del x dx plus del f by del z dz equal to 0. Okay. Now if I rearrange this, what it will give me is dz by dx is equal to minus del f by del x divided by del f by del y. But keep in mind, z is actually a function of x and y. Here we have held y constant. Okay. And because we have held y constant, z appears to be a function of only one variable. But it is actually a function of two variables. So I should be careful and write this as del z by del x. It's not dz by dx, it should be del z by del x. Wait, did I? No. Otherwise, z. Sorry, my bad. del f by del x divided by del f by del z. Okay. Similarly, when x is constant, our differential becomes del f by del y dy plus del f by del z dz equal to 0. And rearranging, you'll get partial z with respect to y as del f by del y divided by del f by del z with a minus sign. Nishit, is this clear? Any doubts?
Yeah, it's clear.
Ashlyn?
Clear.
Yeah, okay. So let's look at two examples. Karthik, is this fine? Okay. If I'm going a bit too fast, let me know, because I have this impression that you have seen this before. This is kind of a basic thing. So I'm just doing one or two examples per idea. It's like a refresher. Okay. All right. So let's say x square plus y square plus z square minus r square is equal to 0. Okay. And the question is to find del z by del x and del z by del y. Okay. If you want, you can do it formulaically. You can write this formula, or you can do it derivation wise, like write the differential and then find it out. Okay. I would rather do it in the derivative manner. Sorry, in the derivation manner, because no one remembers formally. So what I mean is, I'll tell you this: take differential on both sides. Okay. Then take the case where x is constant. Sorry, first take the case where y is constant and you'll get del z by del x. Take the case where x is constant and you'll get del z by del y. That's all. I think this is easy. We'll do it. Rion, can you tell me the differential of this function?
I'm sorry, I didn't get you.
Differential. See, this is of the form f of x, y, z equal to 0, correct?
Yes.
Yeah, some function of x, y, z is equal to 0. And I want you to find the differential of that function, df. So partial with respect to x into dx, this expression.
Yeah.
Okay. Yeah, so do that.
That'll be 2x dx
Perfect.
plus 2y dy
Good.
plus 2z dz, yeah,
This should be equal to
0.
0. Okay. Now, if y is constant, which term will go to 0? In these, out of these three, if y is constant, what will happen? Rion?
Yeah, the y term is equal to 0.
dy becomes 0.
Dy, yes.
So del z by del x then becomes minus x by z, correct? Yeah.
Yeah.
So could you
Yeah.
tell me what del z by del y is?
y by z
Minus y by z.
minus y by z. Yeah.
Nice. Okay. So it's clear, right, what the procedure is? Yeah.
Yes,
Okay.
sir.
Perfect. So we'll try one more, slightly more involved. Uh, e power z plus x square y plus z plus 5 equal to 0. Question is the same. Find del z by del x and del z by del y. Please tell me when you're done. Okay, try this yourself. Tell me when you're done.
Done.
Done. Okay. Yeah. Others also tell me, please. Hi, Ashish. You just joined now.
Yes, sir. 5 minutes back.
Okay. Okay. Karthik,
Yes, sir.
done?
Yeah.
Okay. So let's do it. Let's do the procedure. So first, find the differential of the whole function equated to 0. What is the differential? Tell me. Find the differential of the function. Something into dx plus something into dy plus something into dz will be equal to 0. And the coefficient will be partial with respect to.
2x,
Tell me.
2xy e to the power z plus 1. Sorry,
No.
x square.
X
X
square.
square.
Uh-huh.
X square.
Hmm.
And then e to the power z plus 1.
You got this, right? Did you not start this way? Okay.
Yeah. Yeah, I did start.
All right. Now, so let's find del z by del x. So del z by del x you get by taking y constant. Okay. So if y is constant, rearrange, and can you tell me del z by del x? Karthik.
That's 2xy by e to the power z plus 1.
Minus sign.
Yeah, man.
And del z by del y, Karthik.
X square by e to the power z plus 1.
Okay.
Minus.
Okay, good. All right. So yeah, so I guess this is enough for today. I'm going a little slow because uh, hand in hand we will be doing quantum mechanics also. One is very constant, quantum mechanics is like really challenging to understand. So I'm thinking I'll give one thing that is more meditative. Okay. So you might have, I don't know if you guys have it. I have some nice memories in school. Okay, like not even 11th and 12th. In school, especially in the math classes, we would sit and solve NCRT problems. The problems would be very simple. The teacher will tell us one or two concepts and then tell us how it is done. And then there will be a textbook, there will be textbook problems with slight variations. They'll be kind of the same, but not exactly the same. There will be slight variations and we'll just sit and solve one after the other. It won't be so challenging that it gets frustrating. It won't be that easy, at least for me, that it would be boring. So it was like a game and not very stressful, but very relaxing kind of experience. So I call those meditative problems. Okay. Worse name for it is drill problems, which makes it sound like a disciplined thing, but it's more like a relaxed thing. Okay. So it depends on how much you already know. Okay. If you have seen this before, this will be a meditative thing. If you've not seen it before, it might be a little, you may feel like I'm going fast. But I guess, is there anyone who hasn't ever seen this, this kind of stuff before? All of you kind of knew this at some point. Sarvin, you knew all of this?
Yeah, I think we had like a bit of this like a few sem back. I'm not sure, but
yeah, you might have forgotten, but that somewhere in the back of your mind, it will be there, correct? Perfect. So yeah, that's all. We will stop for today. Tomorrow evening, quantum mechanics, okay? Anyone is free to come, but you are free not to come also. Like the new people, if you can't follow it, you need not come, because tomorrow I'll talk about unitary time evolution. Again, my reference book is Suskind's book only. Okay. I mean, I add other things from various places, but the skeleton I'm following is Suskind's book. You might have noticed, like first 3 chapters are exactly his logic, except the presentation is different. That's all. So next chapter in his book is unitary time evolution, okay, which is what I'm going to do, which we already started one class. I'll just repeat that again, just quickly recap that tomorrow. And then we'll look at time evolution. It's amazing. It's very nice. Yeah. And then day after also, hopefully we'll continue with quantum mechanics, and Monday or Tuesday, we will continue with multivariable. So these two things will go hand in hand. And I don't know if I said this, yeah, Srikanth can't take classes this month. Did I tell this? I had asked you guys that.
no, sir.
No, okay. So I asked you guys to keep time apart for tomorrow, Saturday, for his class. But turns out he has some conference. And because of that, he can't take class this month. And he will be taking next month, vector analysis. So my plan is that by then, for vector analysis, we need multivariable calculus, okay, partial derivatives, multiple integrals, etc. So by then we finish that, so that you can follow his class comfortably. Okay, and in the same time, hopefully we will do time evolution and 1 or 2 quantum time evolution and function spaces. This part I still don't know how to start. I'll figure it out. Function spaces and Fourier series and transforms. Okay, and then we'll solve some specific quantum systems like simple harmonic oscillator, maybe square well, infinite square well. These two, yeah, we'll just do these two. And once we get the function space idea completely, we'll just go a little bit into wave mechanics. We kind of go into our perspective kind of changes now. For certain kind of problems, instead of looking at bras, cats, etc., we'll focus on simply functions and differential equations and possible solutions for differential equations under certain boundary conditions. And then we will, the math of it kind of changes now. Okay, it's linear algebra only, but in the context of functions. And I don't know if like Panchami, I think you were there when we did quantum mechanics from the wave point of view, where we were guessing what the wave function would look like if there is a barrier.
Yeah. I was there.
Yeah. So that's
Well,
go ahead.
barrier, well,
Finite well.
and if it's a free particle.
Yeah. Yeah.
I remember it.
Bound states, scattering states, all those things.
Yeah, it was fun.
Yeah, it's nice, and that intuition is very useful. Okay, the ability to construct wave functions without actually guess wave functions without actually solving an equation. It's very intuitive, and that was one of the questions asked for me in the interview. There was a potential given, like a double harmonic potential, like this. You take two harmonic oscillators, combine them, and you get something like this. And they just said, okay, don't make the thing too pointy here because then derivatives don't exist, etc. And they asked me to guess what the ground state and first excited state looks like. Okay, and yeah, so this is very useful. So it will be nice. So this is actually for me, all of this is like an opportunity to get understand some proper math. Okay, quantum mechanics is a very nice place to learn good math, interesting math in an intuitive manner. All right, so for today we'll stop. See you tomorrow. Thank you.
Thank you, sir.
Bye.
Thank you, sir.
Thank you.
Thank you.